Yeah. I don't know what happened. It was working perfectly, and then it became all blurry. I'm going to send an email out to everybody, making sure that they're joining us. Well, I mean, do I need to send an email? I think everybody's found their way, right? Is there a delay? I mean, we always have this. Okay, please send something on group chat. All right. Very well. I mean, there are only 49 people here. Maybe I'll send an email. Let me take a moment. Questions while we're waiting? We've been practicing multiplication of matrices. For those of you seeing it for the first time, we'll do a few examples. I don't know that we want to do the AIJ necessarily, at least for multiplication. For multiplication, it's a bit technical. On my courses, if you go to the content section, in the content section, there's a links section, and you'll have a link to my courses there. I didn't have time to set up. I'm running late today. I was doing this and that, so many things to do. There may be one or two questions on web work that we have not covered yet. I took a chance and uploaded it nonetheless. We'll probably get to it today. This is so long. All right. All right. I was just sending an email out in case some other people were in. case some people were lost. There was an issue. There was an issue with the quality. Still seems a bit blurry though. Here we go. All right. Let's go back. Let's go back to what we were doing last time. We defined multiplication, you'll recall. And sizes, right? We're really studying matrices as objects in their own right. So let's ask the question, first of all, what are the sizes of each of these matrices? This is a square matrix of size 2 by 2, and so is this one. So multiplication is defined because these two twos are the same. And the multiplication will result in a matrix of size 2 by 2. What is the product here? First row times first column. 2 plus 0 is 2. First row times second column. 0 plus 8 is 8. We've exhausted the columns. We move to the next row. Second row, first column, minus 7 plus 0. And minus 7 plus, 0 plus 5 is 5. Same as the first matrix. Very nice observation, Annie. Thank you. We'll make that observation again very shortly, but very nice. Very nice. We'll give these matrices a name. I'm sure you may, a lot of people may have seen it before. But before we do that, let's do multiplication here. If it's defined, what is the size of this matrix? This is a matrix of size 3 by 1. What is the size of this matrix? This is a matrix of size 1 by 3. So multiplication is defined, and as Annie points out, the resulting matrix will be of size 3 by 3. Absolutely. Let's do it. First row times first column, 2 times 1. First row times second column, first row times third column. Absolutely, Nandini, right? We're going to define this as the identity matrix shortly. We have exhausted the columns. Move on to the next row. Second row, first column. Second row, second column. Second row, third column. And finally, third row, first column. There you go. Let's do one more. about the sizes here. This matrix is of size 2 by 1, whereas this one is of size 2 by 2. So the resulting product of these two will be of size. First of all, the product makes sense, right? Because these agree. And the resulting product will be of size 2 by 1. And then if we multiply it by this, which is of size 3 by 2, that makes sense as well. And then this product is defined because these two agree. And this will result in a 3 by 1 matrix. Absolutely. Now it's telling us to do this product first, right? Because of these square brackets. So let's respect that. First row times first column, 3 minus 2. Second row, first column, 6 minus 1. And finally, first row times first column, 2 plus 5 is 7. Minus 3 minus 30 is minus 33. And 4 plus 0 is 4. There it is. It's a good question to ask. What if there wasn't any brackets? Or what if we multiplied these two first and then this third one? Respecting the order, I claim that you would get the same result. In other words, I claim that multiplication is associative, right? If you're multiplying 3 matrices together, it doesn't matter which 2 you multiply first, as long as the order is preserved. And why is that important? Consider this example here. Consider the following example. Suppose you take 2 matrices, 2 random matrices. Let's take 2 by 2 matrices. 1, 2, 3, 4. And 1 minus 1, 0, 2, let's say. This is a 2 right here, right? But, right, I mean 2 by 2, both of these, so of course the multiplication is defined. Let's do the multiplication, see what happens. First row times first column, 1 plus 0. Minus 1 plus 4, 3 plus 0, and minus 3 plus 8. Nothing spectacular is happening, but let's do the multiplication in the reverse order. First row times first column, 1 minus 3 is minus 2, and already we see what's happening. The product is obviously not going to be the same. Just keep going. First row, second column, 2 minus 4 is minus 2. 6 and 8. There it is. In general, multiplication is not commutative. You know that in the real numbers, it doesn't matter how you multiply the numbers together. 2 times 3 is the same as 3 times 2. Not so in matrices. A times B is not necessarily the same as B times A. Here, right, AB and BA are both defined, but in fact, one product may be defined, whereas the other is not necessarily defined. Right? Imagine a scenario where you had A as a 3x2 matrix and B as a 2x3 matrix. Here the product would be defined and the resulting matrix would be 3x3. And if we did the opposite, B times A, B was 2x3, A was 3x2. So here, BA would be a 2x2 matrix. The sizes wouldn't even be the same. And you can take that a step further. Imagine a scenario where A is 3x2 and B is 2x1. This product makes sense, right? And the resulting matrix would be of size 3x1, but BA, B would be still 2x1 and A would be 3x2. This product is not defined. So that's very interesting, right? This is the first case that you encounter where multiplication is not commutative. It matters very much which way you multiply two matrices. AB is not the same as BA in most cases. Questions here? An obvious question that arises, why this complicated multiplication? Well, let's go back to what gave rise to these matrices, right? We started using matrices as a way to solve systems of equations. Notice that in using this way that we define multiplication, this system of equations can be rewritten neatly into the following matrix equation. 2, 1, minus 1, 4. Notice that this system of equations is equivalent to this matrix equation. Let's convince ourselves. Do this multiplication on the left here. What does this mean? First equation, first row times first column. This means 2x plus 1y. Second row, first column, minus x plus 4y. And what are we saying here? Here we're saying that this 2x1 matrix is equal to this 2x1 matrix. And you know that this is only true if both, if all corresponding entries are equal. So we need 2x plus y to be equal to 3, and we need minus x plus 4y to be equal to 0, exactly the system we started out with. So via this nice way of defining multiplication, we can transform a system of equations into a matrix equation, right? Where in general, if you call this matrix A and you call this unknown, what you're solving for, x and y, let's call this capital X. And if we call this B, right? In general, a system of equations can be rewritten as a matrix equation, AX equals B, where you're solving for X. Now, if these were just numbers, you would easily solve for X by dividing by A, bringing A to the other side. However, these are matrices now, and dividing by a matrix doesn't really make sense. But we'll be able to do the next best thing. Let's put that on reserve for a moment and understand what the next best thing is by observing, as was it Nandini who observed that we had the same thing we began with when we multiplied by the matrix 1, 0, 0, 1? Or maybe it was Annie or somebody else. Out of sight for now. Oh, Annie, here we go. Same as the first matrix. Annie had noticed that when we had multiplied by 1, 0, 0, 1, we got the same as what we started out with. Let's prove it in general, right? If we do the multiplication, A plus 0, 0 plus B, C plus 0, and 0 plus D, right? Multiplying A, B, C, D times the matrix 1, 0, 0, 1 on the right gives you the same thing. Let's do it on the left. Right? First row times first column. A plus 0, B plus 0, 0 plus C, 0 plus D. This is an important observation. Right? This matrix 1, 0, 0, 1, this 2 by 2 matrix, has this very nice property that any other 2 by 2 matrix times that gives you that 2 by 2 matrix back. Multiplying by this matrix is like multiplying by the number 1. You know that if you take any number and you multiply by 1, you get that number back. Here, this 2 by 2 matrix behaves in exactly the same way. A very important property. So let's give it a name. We define this 2 by 2 matrix, which has zeros everywhere except on this main diagonal, to be the identity matrix. The 2 by 2 identity matrix. Questions arise naturally. Do we have the 3 by 3 identity matrix? And so on for larger size. Absolutely. And it's exactly what you would think. Zeros everywhere, except on the main diagonal. If you take any 3 by 3 matrix, A, B, C, D, E, F, G, H, I, observe what happens when you do the multiplication. Right, first row times first column. A plus 0 plus 0. B plus 0 plus 0. C plus 0 plus 0, and so on, right? I'll let you do the multiplication, but I mean, it's trivial. I'm sure you see it already. And same if you do the multiplication the other way. And this idea generalizes to higher dimensions, larger and larger matrices. And they all have the same name. They're all called the identity matrix. It's only the size that changes. Let's give it a name. Definition. The n by n matrix whose entries are all 0 except for ones along the main diagonal is called the identity matrix. Then is denoted IN, n being the size, right, n by n. This identity matrix has the property that if you multiply any matrix by the identity matrix, you get that other matrix back. If A is m by n, absolutely, Britain, yep. It can be any size. So here, if A is m by n, well, the identity should be square, but A can be any, the other matrix can be any size. So if A is m by n, then as long as the product is defined, right? If I want to multiply on the left by the identity, right, since A is m by n, this should be an m here. And this will result in the original matrix. And similarly, A times the n by n identity, because again, you want the multiplication to be defined, that will result in A as well. There it is. Now, consider the following example. Observe that the matrix 1, 1, 1, 2, if you multiply that by the matrix 2 minus 1 minus 1, 1, let's do the product together, see what happens. First row, next first column. 2 minus 1 is 1. First row, second column, minus 1 plus 1 is 0. First row, second row, first column. 2 minus 2 is 0. And minus 1 plus 2 is 1. If you multiply these two matrices together, you get the identity. Notice the other way works as well. All right, first row, first column. 2 minus 1 is 1. 2 minus 2 is 0. Minus 1 plus 1. Minus 1 plus 2. Isn't that nice? Right? Here we're multiplying two matrices together and we're getting the identity matrix. This example motivates the following definition. Let A and B be two square matrices of the same size. B is said to be the inverse of A. If A times B is the same as B times A is the identity. In this case, B is denoted by A inverse. Don't confuse this to mean 1 over A. That would not make sense. It's notation for the inverse matrix. Very much like F inverse is notation for the inverse function. Right, so inverse matrix, inverse function. So what we're saying here, right, is if this is your matrix A, then this is A inverse, because we did the multiplication and we got the identity. These two functions are inverse functions of each other. Consider the following claim. If you start off with a square matrix, if the inverse exists, then there's only one. So there's no ambiguity. Right? There's no ambiguity in calling it A inverse. There's only one. Let's prove it. Proof is nice and slick. What does it mean for two matrices to be inverses of each other? Right? It means that A times B, right? If A and B are inverses of each other, then A times B is the identity. Suppose you have another inverse. Then A times C is the identity as well. What we want to prove is that B and C are the same matrix. Let's prove it. Since these two things are the same, then A times B is the same as A times C. Right? Because they're both the identity. Let's multiply this whole equation by the inverse. Right? The inverse exists. So multiply by the inverse. If you do the same to both sides, then equality is maintained. But let's group these things now, because addition is associative, so it doesn't matter if you multiply A and B first and then A inverse, or these two first. And A inverse times A is the identity. A inverse times A is the identity. And the identity times B, as Annie suggests, is B. And the identity times C is C, because that's one of the properties, well, that's really the defining property of the identity. There you have it. Very nice. So B equals C. And consequently, these matrices were the same to begin with. So why is this important? Well, let's go back to that system of equations, which was now rewritten as a matrix equation. And if we want to solve for x, well, we can do exactly what we did here. Multiply both sides by A inverse. Right? If these had been numbers, you would have wanted to divide by A, but that doesn't work here because it's matrices. But multiplying by the inverse is just as good. A inverse times A is the identity. The identity times x is x. And there you have it. The solution, x is A inverse times B. Another way to solve systems of equations. Well, that's all well and good if you have the inverse of a matrix. What if you don't have it? How can you find the inverse? How do we find the inverse of a matrix? Do all matrices have inverses? Oliver is asking if you have to write all the steps on the midterm. Indeed, you do. Right? The midterm is not going to be testing your ability to plug things into a matrix calculator. Why do we drop the what now in the proof? What did we drop? The 1? Thomas? You have to write all the steps. Yeah, I still don't know. The letter I, the identity? The identity? Well, the identity times any matrix is the other matrix. Exactly. Yeah, Nandini is correct that the midterm, you should expect the midterm to be exactly that. But just know your material, you'll be fine. Oliver is asking if A equals B, can we directly write? There's a slight typo there. I'm sure you meant X equals A inverse B. Let's not. Let's not directly write that, but explain in that case that you're multiplying by A inverse. So we're asking the question, how do we find the inverse of a matrix? Let's take an example to illustrate. We saw what the inverse of this matrix was. It was given to us. But what if it wasn't? What are we looking for? We are looking for a matrix. We are looking for a 2x2 matrix, A, B, C, D, such that when you do the multiplication, you get the identity. That's what we're looking for. So let's do the multiplication. What is the multiplication? First row times first column. A plus C. First row times second column. B plus D. Second row, first column. Second row, second column. So we're looking for A, B, C, D such that this is equal to that. These are two 2x2 matrices, and the only way they're going to be equal is if the corresponding entries are equal. So if A plus C equals 1, and if B plus D equals 0, if A plus 2C equals 0, and if B plus 2D equals 1. That's what we're looking for. We're looking for A, B, C, D, which satisfy these two well, these four equations. But here you have a system of two equations, two unknowns. And same thing here. So we can use matrices to solve for that, right? You know it's a system of two equations, two unknowns. So if we use matrices to solve for that, we'll reserve the first column for the A's, second column for the C's, and same thing here. 1A plus 2C equals 0. So you could row reduce this till the end and find your A and C. But hold on. Let's do the same thing here. Let's set up an augmented matrix solving for this, where we'll reserve the first column for the B's, second column for the D's, and then the constants. So B plus 2D equals 1. And now take a step back. Right? I mean, you could row reduce this to reduce row echelon form and read off the solution. You could row reduce this to reduce row echelon form and read off the solution. But if you take a step back, notice that this matrix, right, this 2 by 2 matrix here, is the same as this one. So, you know, we're going to be smart. We're going to be smart, and, you know, we're not going to do things twice for no reason. We're going to think about this. We're going to say, why don't we, right, you've got the 1, 1, 1, 2 thing. Why don't I do the same thing, just throwing in that other column at the end? Right? I mean, it seems very smart. Seems like the smart thing to do. And when you row reduce this to reduce row echelon form, if this is the 1, 0, 0, 1, then A will be this, C will be whatever's here, and then B will be whatever's here, and D will be whatever's there. And if you remove this line here, what are we really doing? We are starting with a matrix, and we are augmenting by the identity. If you row reduce this and you get the 1, 0, 0, 1 business, in other words, if you row reduce to get the identity, then whatever's here is going to be the A, this is going to be the B, C, and D, A, B, C, D. This is going to be the inverse. If you're able to row reduce your matrix to the identity, then the inverse will be on the right. Let's do it. And in fact, this gives us a condition for the inverse to exist. For the inverse to exist, your function has to row reduce to the identity. So we're starting with this. Let's row reduce. So now you see what's happening, right? Row reduction is back to haunt us. If you weren't already an expert in row reduction, it's just going to be worse from now on. So if you're still not yet an expert in row reduction, you have to get to it. Let's row reduce. We've got a 1 here. I'll use that to clear out the column. Row 2 minus row 1 for row 2. So first row remains unchanged. Second row, minus 1, 2 minus 1, minus 1 and 1. And let's use this 1 to get rid of that one. Row 1 minus row 2 for row 1. This minus that. This minus that. There it is. This matrix is the inverse of the original. Exactly as we knew it was, right? Because we had started by taking the product of this and the original one, and we saw that the product was equal to the identity. How are we doing? Shall we take a few examples from the book? Taken from page 101. The question is asking us to find the inverse if it exists. I mean, are you talking about row 2 minus row 1 for row 2? I want to see this on an exam. I want to see this on an exam. The marker has to understand what you're doing. If the marker cannot follow along, yeah. Before that step, what did we do before that step? We just wrote the original matrix down and augmented by the identity. Oh, so when I remove that vertical line, you mean that's not going to be important. That's not going to be important. The idea is this, right? I mean, you start with your matrix and you augment by the appropriate size identity. We went through the justification in class, so you never have to go back to that. You can right away jump to there. Absolutely. But in the row reduction, I want to see every single step. You know what to do, right? We're going to use this leading 1 to clear out the column. Row 2 minus 7 row 1 for row 2. Let's change this minus 4 into a 1. I trust everybody's with us here and you're able to do these row operations as quickly as I can. Let's finish it up. Row 1 minus row 2 for row 1. leaving us with 1 minus this minus that. And there it is. We're suggesting that if we call this matrix A, then this is its inverse. And let's verify, because again, here you have the opportunity to verify your work. Is this right? Is this really the inverse? If you multiply the two matrices together, it should give you the identity. Let's do it. See what happens. Minus 3 over 4 plus 7 over 4 is 4 over 4, which is 1. 1/4 minus 1/4 is 0. Minus 21 over 4 plus 21 over 4 is 0. 7 over 4 minus 3 over 4 is 4 over 4, which is 1. Very nice. Theoretically, you'd have to check the other way around, but let me offer a theorem. If A and B are square matrices of the same size, and A times B is equal to the identity, then the other way will be true as well. So if one product is the identity, so is the other one. So you don't actually need to check both ways, even though you know in general multiplication is not commutative, right? AB is not equal to BA. Normally, it is true if they are square matrices and the product is the identity. How are we doing here? Questions? Shall we do a few more? The identity times A is just A, absolutely. Same question, we're looking for the inverse here. So you know what to do. We're going to augment by the appropriate sized identity and row reduce. You know what to do. I'll let you get started. Can we invert? You mean interchange row 1 and row 2? No problem there. Absolutely. In fact, let me use this one to clear out the column first, and then I'll switch. So row 1 plus 3, row 2 for row 1. And then I'll switch row 1 and row 2. So this plus 3, this plus 3, this plus 3, and this plus 3. Yep. Row 1 interchange with row 2, nothing wrong with that. And let me finish it up by saying row 1 minus 3 row 2. 4 row 1. There we go. Alfari, glad I could be of help. Could we have done row 1 plus 4 row 2? Yeah, absolutely. Row 1 plus 4 row 2. Nothing wrong with that. It's an allowable row operation. So as long as you're using allowable row operations, it's all good. This will lead to the same answer in the end, and we're fine. So again, if this is the matrix B, then the inverse is proposed to be this if no mistakes have been made. Again, we can check. We can check by multiplying the 2. This times that, when we get 9 minus 8 is 1. 24 minus 24 is 0. Minus 3 plus 3 is 0. Minus 8 plus 9 is 1. And as Ben pointed out, this matrix is its own inverse. Isn't that a nice observation? B is the same as B inverse. The matrix is its own inverse. Very nice observation, Ben. There it is. So you see the beauty here, right? I mean, you do some work, you find the inverse, and then you can check that you're correct. Let's try another one. Nandini is asking if I prefer calculus to linear algebra. Here's the thing. Calculus is more straightforward. And I like straightforward. But linear algebra is so amazing. And you don't really see how amazing it is when you're doing it, when you're doing a first course like 123 or even 133 for those doing a more advanced, much harder course. But when you're in that course, you don't see how every single thing you ever do can be rewritten in terms of linear algebra. Everything you do has a linear algebra counterpart. It's completely insane. And if you encounter something that doesn't, that's probably because nobody's been able to do it yet. But almost anything you want to do can be rewritten in terms of linear algebra. The derivative can be rewritten in terms of matrices. I proved a few years ago, because I know, well, for those of you familiar with series, I proved that you can use matrices to find what some series converge to. So Sophie is suggesting that this one has no solution, and you're absolutely right. Right, we're looking for the inverse. So we would augment by the identity and row reduce. Maybe let's divide by 5 here. 1/5 row 1 for row 1. 1, 2, 1/5, 0. And as we suggested, a matrix has an inverse if and only if you can row reduce it to the identity, right? In other words, if you can solve for the ABCD and a simple next operation here, row 2 plus 3 row 1 for row 2, gives us a row of zeros here. 3/5 and we're in trouble. We're in trouble. This is in reduced row echelon form. This is not the identity. So the matrix, this is the simplest form the matrix can have. The matrix does not have an inverse. Let's do one more. We've been doing examples in the 2x2 case, but of course this scales up, right? 3x3, 4x4, 5x5, and so on and so on. We're looking for the inverse of this 3x3 matrix. The process is the same. We're going to augment by the appropriate size identity. In this case, by the 3x3 identity. Row reduce. If the reduced row echelon form of the matrix on the left is the identity, then the inverse will be on the right. If the reduced row echelon form is not the identity, the matrix will not have an inverse. All right. Maybe use this one to get rid of that one. Row 3 minus row 1 for row 3. Thank you, Annie. All right. Whatever you want to do. What do I want to do? I don't know what I want to do. Let me use this 2 to transform this into a 1. Just for fun, it seems like the thing to do. Row 2 plus row 3 for row 2. That's what I was thinking as well. And normally that's what I wanted. That's what I would have done. Somehow I feel that I want to mix it up. So let me propose this. An XC can do that operation, and some of you do as well. And let me try row 3 plus 2, row 2 for row 3. So row 2 remains unchanged. This becomes a 1. I'm adding 2 of those. Adding 2 of those, you get a nice 0 there. And now let me use this one to clear on the column. Row 2 minus 2 row 3 for row 2. Row 1 minus 3 row 3 for row 1. And then maybe interchange row 2 and row 3. So this minus 3, this minus 3, this minus 3. This minus 2, this minus 2, this minus 2, this minus 2, and this minus 2. Leaving me with the 1 operation, negative row 3 for row 3. Well, I'm sure you don't want to rewrite all of that. There it is. But since we're not too lazy, let's check that we have not made a mistake. Let's do the multiplication. 4 minus 3 is 1. Minus 6 plus 6 is 0. Minus 3 plus 3 is 0. Minus 2 plus 2 is 0. 4 minus 3 is 1. 2 minus 2 is 0. 4 minus 4 is 0. Minus 6 plus 6 is 0. Minus 3 plus 4 is 1. Beautiful. You do not have to verify your work on the midterm. I strongly encourage you to verify your work on the midterm. You'll have 72 hours. Why would you not? You know, you don't even have to submit that verification. You can do it on the side. Exactly. I mean, unless it's asking you to verify, then you don't have to. And as suggested, you could do it on the side and at least, have peace of mind, which is what everybody wants, right? How are we doing here? Questions? So practice this finding inverses, and we'll pick this up again next week. You guys have a good weekend. Thank you all for coming, and I will see you then.